Good day, class. In this lesson, we're just going to look at a single example of implicit differentiation. So be sure to look at the previous lesson to make sure you understand why we need implicit differentiation. In this example, we're asked to find the derivative of 9x squared y plus 5xy squared equal to negative 9. So if we want to differentiate the standard way, we need to solve this equation for y. We need to get y all by itself. And then for every solution available for y, we would need to find the derivative. And that could be multiple instances of finding the derivative. And that works every time. However, implicit differentiation says that there's an easier way. Rather than solving for y and then finding the derivative of multiple sections of this particular, if it were in a graph form, you would see, then we could find instead just the derivative of this entire thing in one shot. So let's do that. That will then be implicit differentiation. And so we're going to start by taking the derivative of both sides of the equation. So that's what we always do when we begin implicit differentiation. So all I've done at this point was indicate that I'm going to take the derivative with respect to x, and that's the kicker here, taking the derivative with respect to x of both sides of this equation. And so this is just notation. So then in the next stage, I need to actually begin to do that. But it's a little tricky for me. So I will just maybe break it up a little more. Based on the sum rule of differentiation, we know that we can take the derivative of 9x squared times y plus the derivative of 5xy squared on that left side. And of course, the derivative on the right side of the equal sign is there's just one term. So we're just taking the derivative of that. So all I've done at this point was just apply the sum rule that says I'll take the derivative of both terms in that sum. So still a lot is going on here, but all I've done was indicate that I'm going to take the derivative of each term. And so now I actually recognize that I need to take the derivative of this term. I need to take the derivative of this term, and I need to take the derivative of this term. And so I'll do that. But in each instance, I need to recognize what it means to take the derivative of each of those terms. And I'll go from left to right. So in the first term on the left, the 9x squared y, if I take the derivative of that, I should recognize that the product rule is necessary because I have a product. Okay, so I'm going to take the derivative of 9x squared y with respect to x. Of course, I'm taking the derivative with respect to x. So in order to do that, I'll employ the product rule. And the product rule just says, I'll pull out that 9 and it will help me just because the differentiation rule of constant multiple says I can just move that, or I can just move that constant out of the way and just deal with the x squared y. So I differentiate x squared y by way of the product rule. So that x squared becomes 2x times y, nothing happens to y, plus this time I'll leave x squared like it is, and I'll find the derivative of y, which is just 1. Okay, so that's all that's happened up to this point. But notice I left some extra space beside where that y has been, where I found the derivative of the y, because I actually had to take the derivative of y. But I was taking the derivative of y with respect to x, so I have to indicate that. Okay, so when I took the derivative of that y, I'm indicating I took the derivative of y with respect to x. That's all I'm doing here. I'm just putting or adding that feature that lets us know we haven't taken the derivative of y with respect to y. So that still needs to happen. And so I can just do that with notation and just call it the derivative of y times dy over dx. Okay, and so that will give me the latitude that I need to move forward. Okay, so I'll do the same thing with my next term. Okay, so my next term is 5xy squared. So the same thing. Move that y out of the way and just deal with the x times y squared. Okay, so once I do that, I have y, or I have my x becomes a 1 because I differentiate that. My y squared just sits there because that's how we operate with the product rule. The x just sits there, and the net plus, then the x just sits there. It doesn't get differentiated. And then the y squared gets differentiated, but I'm talking about with respect to x, so I need to indicate that and call that actually 2y dy over dx. And so that gives us, again, the latitude to move forward, and just note that this has not been differentiated with respect to x because we're talking about 2y. And then the other side of the equation, fortunately in this example, that's pretty simple. We just go forward with the differentiation of -9, which is 0. And so now I've done most of the dirty work. All I need to do is simplify. So take a minute to pause this video and just notice how I just simplified everything. Just show what multiplies by what, or what simplifies, or what happens. And then in my next stage, I'm going to simplify more. Notice how I distributed that 9 and I distributed that 5. That's all that has happened. And then in my next stage, I'm looking to solve. Okay, so all I've done was simplify, then I combined my like terms, and then I'm looking to solve for dy dx, because that's what I want. I want dy dx, the derivative of this entire function. So dy dx is what I'm looking for. So I'm solving. So in this next stage, I've just subtracted from both sides of the equal sign -18, or I've subtracted 18xy from both sides of the equation, and I've subtracted 5y squared from both sides of the equation. That's all that has happened at this stage. Now I can continue on. I'm still trying to get dy dx by itself, so I can factor that out and show what's left behind. All I did was factor that out and leave what was left behind inside the parentheses. Now I can divide both sides by that factor, 9x squared plus 10xy. And of course, as I intend, that 9x squared plus 10xy on the left cancels. And so I'm just left with dy over dx in the equation on the left, which is my objective. I have dy over dx all by itself. So that's my solution. This is the derivative of my original equation.